Bismillahirrahmanirrahim. Welcome back with the fifth lecture. Now, in this lecture, we will discuss about the set theory 1. We introduce, first of all, we give some introductions to set theory 1. And this is the today's lecture's outline. Why we study set theory, sets, operations on sets, memberships, notations, and Venn diagrams. This is the first question, so that why we study set theory. Understanding set theory helps us to see things in terms of the systems, organize things into groups, begin to understand the logic. These are the basic key points of the set theory. Because of that, we study this topic. What are the sets? A well-defined collection of distinct objects is called a set. Or a set is a gathering together into a whole of definite distinct objects of our perception and of our thought, which are called elements of the set. Actually, you can see that it's a collection of defined different objects. If the objects are undefined, then we can see that that's the empty set. Empty set is also a set, but things are not defined. The elements or members of a set can be anything. You can see that the elements are numbers, people, letters of the alphabet, other sets, and so on. Sets are conventionally denoted by capital letters. We denote them by the capital letters A, B, C, up to so on. And the objects which are in that sets are called the elements, are called entries, or maybe you can call them members of the set, entities of the set, members of the set. You can say sets are denoted by the capital letters A, B, C, X, Y, Z. The elements of sets are represented by the lowercase. If you want to represent elements, you can use the lower letters A, B, C. If we use in this as a set, and the notation is used for set is the capital letters, and sets are defined in between these two brackets. So, for example, A is a set where the elements are tiger, lion, puma, cheetah, leopard, cougar, so on. So this is a set of large species of cats. We can say that A is a set of alphabets. This set is consisting of the lower cases of the alphabet, lower letters. And if we can say that A is equal to -1, -2, -3, this is a set of negative numbers. So these are all the examples of set. In all above examples, each element of the sets is distinct and well defined. So in the following examples, we write the sets in tabular form. If the set A is equal to 1, 2, 3, 4, 5 is a set of first 5 natural numbers. B is a set of even numbers, first 50 even numbers. And C is a set of positive odd numbers. We can write all these sets into tabular form and descriptive forms. What is descriptive form? Now we will write the previous slides examples in the descriptive form, where A is a set of first 5 natural numbers, its descriptive form. We write in the previous example A is equal to first 5 natural numbers. We write 1 to 5. 1 to 5. Now in descriptive form, you can describe. Actually, you can say that you describe the sets. So set of B is a set of positive even integers less or equal to 50. B is the set of positive even integers less or equal to 50. It's also descriptive form. C set of positive odd integers. So set of odd positive integers C, which we write in the previous example, C is equal to 1, 3, 5 up to 49. So set of positive odd integers less than 50. If we write it into the set builder form, we can say that A is equal to x. X belongs to the natural number n such that x is less or equal to 5. This is for first example A. It is set builder form. And B, the set of positive even integers less or equal to 50. So we can write x is equal to its B is equal to x belongs to E. E is a set of even integers such that its 0 is equal to 0 means you can say that even or odd. So between 0, x is between 0 to 5. So this is the set builder form. Now we discuss about the operations on sets. First of all, union. Two sets can be added together with the union of A and B denoted by A union B is the set of all things which are members of either A or B. It means it's addition. You can add from both of the sets, either from A, either from B. So A union B is actually the element x belongs to U such that x belongs to A or x belongs to B. X belongs to any of sets A and B. For example, if A is equal to A, C, E, G and B is equal to D, E, F, G, then A union B is equal to X belongs to union, where X belongs to A or X belongs to B. It means both A, C and B from this B, E, F and G. We have to be careful about the order of the numbers. We write in descending, ascending order, especially. A union B is equal to this. So A, B, green, if a union of red, white, green. So 1, 2, red, white, green. This is the union of these two sets. So if we take the union of 1, 2, union 1, 2, then both sets are same. So union is only one set, A, B, A or B. So we write one element from both the sets. Intersection. A new set can also be constructed by determining when whose common two sets have in common, whose elements are in common. A intersection B is equal to X belongs to U such that X belongs to A and X belongs to B. If the element belongs to the both of sets, then it's is written in union in intersection. The intersection of A and B, denoted by A and A intersection B, is a set of all things which are the members of both A and B. So if A intersection B, it means then A and B are said to be disjoint. They are totally different. If one element from A and B is common, then A intersection B is not equal to 5. For example, 1, 2, we take intersection with red and white, so it's empty. 5 shows the empty. So there is no common thing from both the sets. So A is equal to A, C, E, G and B is equal to D, E, F. If we take this, then the common elements from these two sets A and B are E and G. And if we take the 1, 2 same sets 1, 2 and 1, 2, then the intersection is one set and the union is also one set. Complements. Two sets can also be subtracted. The relative complement of B in A, also called the set theoretic difference of A and B. This is denoted by A slash B or A minus B. It may be written as this. Is a set of all the elements which are the members of A but not the members of B. It means that we subtract the elements from A minus B. We have to note that it's valid to subtract the members of a set that are not in the set, such as removing the elements green from the set 1, 2, doing so has no effect. So if we take 1, 2 from minus from red and white, so it's 1 and 2. And if we take 1, 2 green from red, white and green, then 1, 2 is are the elements which are not in B. Green is common, so we can't take it in the in the different set. If U is the set of integers, then there exists a set of even integers and O is a set of odd integers, then the complement of E is even set is O. Cartesian products. A new set can be constructed by associating every element of one set with every element of another set. The Cartesian product of two sets A and B, denoted by A cross B, is a set of ordered pairs, such as A is the member of A and B is a member of B. For example, we write 1, 2 with the Cartesian products with red and white. So we take 1 with red and 1 with white, then we take 2 with red and then 2 with white. So it is the Cartesian product of these two sets 1, 2 red, white. If we take Cartesian product of 1, 2 green by red, white and green, then we take same as in previous example, 1 red, then 1 white and then 1 green, and then 2 red, 2 white and 2 green, and then green red, green white and green green. So the elements in the uh, in the Cartesian products are uh, if there are two elements in A and two elements in B, then the number of elements of Cartesian paired ordered pairs are 4. Similarly, if we take 1 2 Cartesian product by 1 2, then it's 1 1 1 2 2 1 and 2 2. Special sets. There are some sets which hold great mathematical importance and are referred to with such regularity that they have occurred special names and notations, conventions to identify them. One of them is empty, which I have already discussed with you people, and it's denoted by these brackets or simply phi. This is the sign of bracket signs for sets, and there is no element in this set, so this is empty set. It may be represented as phi. Another is the singleton set X, which contains exactly one element. If it contains only one element X, so it's singleton element. If any set which have only one element, then the set is called singleton set. P, or denoted by this P, denoting the set of all primes 2 3 5 17 up to so on. N is a set of all natural numbers 1 2 and so on, and Z denoting the set of all integers where positive, negatives, and Q is the set of rational numbers A or B. This is the definition of rational number which I have discussed in the previous lecture. Q are the Q have the elements A or B, where A B belongs to Z and B is not equal to 0. And R denoting the set of all real numbers. This set includes all rational and together with all irrational numbers. Irrational numbers, which I have discussed already, that is numbers which cannot be rewritten as fractions, such as pi, e, 2 square root, as well as the numbers that cannot be defined. I have already discussed in the previous lecture. You can read from the lecture 4. C, denoting the set of all complex numbers. Complex numbers may be defined as a plus b iota, where iota is the complex and ab both belongs to the real number. For example, 1 plus 2 iota, this is a complex number, it belongs to C, and iota is equal to minus 1 square root, and if we write iota square, it's equal to minus 1. Finite and infinite sets. A set is finite if it contains a specific finite numbers of elements. That is, if we can count the element in a set, such sets are called finite sets. Finite sets, for example, some finite numbers in set, the number of digits on your hand, the number of seats on a bus, and the number of people on earth. These are finite. Infinite set, a set is said to be infinite if it is not finite. For example, the set S of letters in alphabets is finite and the numbers are 26. Infinite sets, the set of positive integers, they are infinite, 1 2 3 continue. So this is infinite. If you can say the number of hairs on a head is also finite set, is infinite set. The number of fingers in a hand, this is finite, you can count the fingers. So that sets that can be counted are finite sets that cannot be countable, so that are infinite sets. Finite and infinite sets, set definition: x, such that x is a lowercase letter. So cardinality, we define here cardinality. Cardinality basically is the number of elements in a set. The cardinality of A is 26 because the lowercase letters in alphabets is 26. So we can say that cardinality of A is 26. Now B is a set of these elements. So the cardinality of set B is 1, 2, 3, 4, 5, 6, the number of elements. Okay, and C, x is an even number which is less than 10. So the number of elements which are even and less than 10 are 4. You can write 2, 4, 6, 8, not 10, because there is a condition that x is even and less than 10. So the number of even numbers which are less than 10 are 4, 2, 4, 6 and 8. So the cardinality of C is 4. A is a set of natural numbers, so the cardinality is a set of natural number n. So x is a point on a line, so these are also infinite. X is a point in a plane, these are not countable, so the cardinality of C is undefined. Memberships. The key relation between sets is membership. When one set is an element of another, if A is a member of B, this is denoted by A belongs to B. If one set is one element is from any element, if we take a set is equal to 1, 2, so we can write that 2 belongs to A. It means 2 is the member of this set A. While if C is not a member of B, then we can write C doesn't belongs to B. For example, with respect to the sets A 1, 2, 3, 4 and B blue, white, red, so 4 belongs to A and green doesn't belongs to B. So this is the examples of membership. This means belongs. The universal set is the set of all things relevant to a given discussion and is designated by the symbol U. That is, it contains every set. Subsets. If every member of a set A is also member of set B, then A is said to be a subset of B. You can write you can say if officer, a chairman, which and the employee which are working in their leadership, in his leadership, so the employees are the subsets of that chairman. And we can write A subset of B, also pronounced A is contained in B. The elements between the sets established by this is called the contained the elements. So it means the elements of A belongs to the elements of B. So A is subset of B, and B is the superset of A. For example, A is equal to 1, 2, 3, 4 and B is 1, 2, 3, 4, 5, 6 and C is equal to this, then the universal set U is equal to, which contains all these three sets 1, 2, 3, 4, 5, 6, 7, 8, 9, and all the sets A is also the subset of U, B is also the subset of U, and C is also the subset of U. Superset. If we can write B superset of A, read as B the superset of A. It means B includes A or B contains A. You can say the converse of subset, this proper subset. Let A and B be sets. A is proper subset of B if and only if every element of A is in B, but there is at least one element of B that is not in A and is denoted by A. It means that is no element which, so equality, when we vanish equality, then it is proper subset, and if we write equality, then it's improper subset. For example, the set of all men is a proper subset of the set of all people. Let A is equal to this, B is equal to this, then A is a proper subset of B, because all the elements of A contained in B. There is an element B, 2 of B which is not in A, 1, 3 is a proper subset of this, and if we write this these sets, so you can see that they may be equal, 1 2 3 4, the same elements, so these sets are improper subsets of each other. An obvious but useful identity which can often be used to show that two uh, different sets are equal, A and B, A equal to B if and only if A is subset of B and B is subset of A. Mean to say both A contains all the elements of B and B contains all the elements of A. Power set. The power set of A is the set containing all possible subsets of A, including the empty sets. So it contains 2 to the power n elements, where n is the number of elements in A. It's typically denoted by power of A or 2 power of A. For example, the power set of A, B, C, D is a set. We can write all the subsets of A, which is A, B, empty, A, B, C, D, and then we write A, B, A, C, A, D, and then C, D, C, A, C, B, C, D, and then A, B, C, and after all we can write all these elements. So if here the number of elements are 4, so 2 raised to the power 4, 16. 16. You can count all these subsets which are contained in the power set. So these are 16. So if we have a set A which have only 2 elements, so in the power set of A, elements are 4. Subset relationships. If A is a set such that x is a positive integer which is less or equal to A, then set A contains 1, 2, 3, 4, 5 up to 8. And if we write that not equality, then 8, we can vanish 8 from this. If B is a set such that x is a positive even integer and less than 10, set B contains 2, 4, 6, 8. And C is a set 2, 4, 6, 8, 10, then set C contains these elements. So the universal set is this 1 to 10. So subset relationships, if we write from these sets, A is subset of itself, every set is a subset of itself, and improper subset, note that this is, and A is not improper, is not proper subset of B. You can see from this, A is not proper subset of C, B is the proper subset of C. You can see B is the subset of C and C is also subset of C. C doesn't proper subset of A. C is not proper subset of this, and C is not proper subset of B. equal sets. Two sets A and B are equal if and only if every element of A is in B and every element of B is in A, and is denoted as A is equal to B. Two sets mean to say the every element of A is in every element of B. You can A is proper subset of B and B is proper subset of A. So you can say that A is equal to B or B is equal to A. You can rearrange all these elements, but the number and the elements should be same. Let A is equal to this and B the set of positive integers, positive divisors of 6. So C is equal to 3, 1, 6 and D is equal to this. Then A, B, C and D are all equal sets. Here are some notations, symbols and meanings. Uppercase designates the set name, lowercase designates set elements. These brackets enclose the elements in sets. This means belongs to or not. If we take a line, then it's this is a subset with equal subsets. Is the proper subset of this means does not subset of this symbol is for superset, and this line shows that such that if a condition, and this line shows the cardinality of set. Venn diagrams, which is very important, we discussed here. Venn diagrams are set diagrams, are diagrams that show all possible logical relations between a finite collection of sets. Venn diagrams were conceived around 1880 by John Venn. Venn diagrams show relationships between two sets and their elements. If there are two sets, this set is A and this set is B, and this is the universal set. The Venn, if we color them, the Venn diagram shows that this universal set contains both the sets A and B, and if any portion is common, then we can overlap these diagrams. Then this will show that the intersection part or union part of any two sets. Now here is the example. If A is a set of positive integers and x less or equal to 8, it means positive integers less or equal to 8. So these are 1, 2, 3, 4, 5, 6, 7, 8, and B is the set which is even and less than or equal to 10. So these are even, x is even, so 2, 4, 6, 7, 2, 4, 6, 8 and 10. This means if we take A, this is A and this is B, the common points are 2, 4, 6 and 8. So these are the common elements. So we can highlight it with a yellow color, and this shows that A is not subset of B, proper subset, and B is not proper subset of A because this element is not contained in this. So another example you can see here, if A is the set of integers which are less or equal to 9, so these elements are 1 to 9, and if B is the set of integers of even integers and less or equal to 8, these are this. So these elements 2, 4, 6 and 8, these all contains in A. So this is A set and it contains B. So B is the proper subset of A and A is the proper superset of B. A is not proper, is proper subset of B. A is a superset. Another example, you can see this is A, X is even, this is A is the set of positive integers where X is even and less or equal to 10. So the elements of A are 2, 4, 6, 8 and 9. If we take B as the set of positive integers and X is odd, which are less than, so these are 1, 3, 5, 9. So there are no common points between these two elements. Here we can't write 9, we can write 10. It's an error, please correct it. It's 10, not 9, because here is the condition of even and equal to 10. So there is no element in these two sets which are common, so we can write this is A and this is B. So the common region is empty. You can write A is not subset of B and B is not subset of A. Set operations: A intersection B, A union B. These are the two set operations. A intersection B is a set where X are the elements, X belongs to A and X belongs to B. This is the intersection of A and B. And in union, you can add both the elements, either they are from A and they are from B. Set operations and Venn diagrams. From this Venn diagrams, we can understand the set operations. Let U is A, B, C, D, E and F, and A is equal to A, C, E, G. These are the elements of this set, and B are D, E, F and G. So A intersection B is equal to E, G. So this is the area which shows the intersection of A and G. So we can write A intersection B such that X belongs to A and X belongs to B. These are the elements which belongs to both of the sets from set A and set B. Here we take the example of union in Venn diagram. So if we take A as A, C, E, G and B, D, E, F, G, if we write A union B, we can write as X belongs to U such that X belongs to A or X belongs to B, and A, B, C, D, E, F. This is the union set. The union means it contains either all the elements that are from A, either from B. A union B is equal to the element X such that X belongs to A or X belongs to B. So in union you can add from any of the element, and in intersection you can say that you have to only write the common elements from both the sets. Uh, Another set operation by in Venn diagram is the difference. You can write A minus B is equal to the set X such that X doesn't belong to A and X belongs to B. If let U is equal to this A, B, C, D, E, F, and A is equal to A, C, E and F, and B is equal to D, E, F and G, then A minus B, we subtract all elements that are not in A, all the elements of A B from A that are not in B. So these are A, C. This is the uh, set operation on Venn diagram. A, C, it means complement. This C means you can write this as U minus A complement. You can also write it as A dash, means A complement. It complement means universal set minus that set. That's the set with the element X, and X doesn't belongs to A and X belongs to union set, universal set. If the universal set is this A, B, C, D, E, F and A is this, then AC, you can write this C here not, but in superscript as in power. So AC U minus A. So B, D and F, which are not in A, these are the elements in their complement. So be careful about this. It can be written as A dash. Sets and universal set. If A is equal to 1, 2, 3, 4 and B is equal to 1, 3, 5, 7 and C is equal to 7, 9, 3. These are three sets. If we take these are three sets, and a universal set is this 1 to 9. Locate all these information appropriately in a Venn diagram. We can locate it into Venn diagram. This is the solution of these. U is the whole set which contains all the elements A, B and C. This is A, which contains some part of B and C. You can see that 1, 2, 3, 4, 3, 1 and 3 from 1 and 3, they are also in B. And C contains 7, 9, 3. So 3 is also common in B and C, and the universal set is the whole set. This is another example for the Venn diagram. You can write 1. These are the elements 1, 2, 3, 4. 1 is the common, which I have already discussed. You people, 1 is common in C and B. 1 is common from C and 3 is common from C. 3 is common in C and A. And if we take A and B, 1 is common in A and B. And if we take B and C, so 7 is common. 7 here also in C and here also in B. So 7 is the element in this, and these elements 6, 8 doesn't belong to any these three sets A, B, C. So these are the elements. These all are the elements of universal set, but these elements doesn't contain in any of A, B, C. So we can write from these diagrams out of these circles. Now sketching regions representing sets, though we can sketch the region corresponding to the set A union B complement intersection C. You can focus on this set B complement A union B complement intersection B. So this is the universal set. These are 1, A, B and C. These sets, the here are A, B and C. We can write all these three sets in we can sketch to clarify this expression. Uh, Now we here sketch A union B complement intersection C. These are the elements, these are the sets A, B, C. Here we sketch. So A in union B complement. So this area intersection C. So which area is the common from both these A union B complement and C. Here we sketch the region corresponding to the set A union B intersection C. This is the area of A union B intersection C. Here A union B complement. This B complement mean U minus B complement is equal to U minus B. So this is the area, and this which can be subtracted from this. Here in this slide, I am trying to show more Venn diagrams A intersection B intersection C. So A intersection B intersection C is listed. A union B union C is shaded. Here in this diagram you can see all the shaded region. A minus B intersection C, you can see these this area. A minus B union C is shaded here in this diagram. uh, Providing set identities by Venn diagrams, you can prove all these. A minus B is equal to A intersection B. A minus B is equal to A intersection B. You can prove all these from these slides, these Venn diagrams. A is equal to 1, 2, B is equal to 2, 3, and A minus B is equal to 1. So this proves this statement. You can prove all these from these Venn diagrams. And in B, A minus B is the shaded region. If this A is equal to 1, 2, and B is equal to this, and A minus B, this is the shaded region. And in A minus E, this is shown in this diagram. So at the end of this lecture, we present here the lecture summary. Why we study set theory, uh, and we briefly describe this in the previous slides. And sets, especially the definition of sets and different notations used in sets, and how can we express the sets, and how can we present in set builder notation, and operations on sets, especially we discussed here in this lecture. Union, intersection, difference, complement, all these operations were discussed in this lecture. Membership, we also discussed here in this lecture. Membership belongs to, does not belongs to, subset, proper subset, improper subset, proper subset, and when the any element, and when any set which is not subset. Notations, we discussed here notations. And the last one but not least, especially the Venn diagrams, which we discussed here in the last of the lecture. Venn diagram, we draw some diagrams A and B. If there are two sets A and B, then how can in the union, intersection are graphically represented by the Venn diagrams. we discussed here.